So today we're going to look at recursive and explicit formulas for geometric sequences. Just to give you some examples, a recursive formula is one that relies on a previous term. So here we have a1 equals some number and a to the n equals a to the n minus 1 times some constant. For explicit, it's a formula that gives you any value of a to the n. So n could be anything. We could look for a to the 203rd, and we'd be able to find it using the explicit formula by just doing one calculation. So for your first example, you had a geometric sequence of 4, -20, 100, and -500. So seeing that, we know that a1 is 4, so a to the n is going to be a to the n minus 1 times some constant. So between these two, looks like you multiply by a -5. Again, you multiply by a -5 and multiply by a -5. So it looks like our a to the n is equal to a to the n minus 1 times -5. And that's our recursive formula. For explicit, we want to write it in the form of a to the n equals something that relies on n, not a to the n minus 1. So again, between each number, you multiply by a -5. So we know that when we start with 4 and multiply by a -5, we want to get 20. So if 4 is the first n, we want to make sure multiplying by that -5 gives us a 4 again. So if n equals 1, this becomes 0. -5 to the 0 power is 1. So a to the 1 is equal times 4 times -5 to the 0 power, which is just equal to 4. So it works out for that one. If we want to check a2, you'll get 4 times -5 to the n minus 2, which is 1. So that's 4 times -5 gives us 20. We can check a3. So 4 times -5 to the n minus 2, to the 3 minus 1, which gives us to the second power. So -5 times -5 is 25. 4 times 25 is 100, so that worked. And then a4 is 4 times -5 to the 4 minus 1, which is 3. So 5 times 5 is 25, times 5 is 125. So 4 times 125, which gives us, negative 125, which gives us -500. So that is the explicit formula. It works for all those cases. We just multiply by a constant in order to end up with the -5 to the n minus 1 power. So then you had another question that wanted you to write the explicit formula based on this recursive formula. So I like to use this little table. So let's use x and f of x and just set up a few numbers. So we know f1 is 8, and then let's do 2, 3, 4, and 5. So 2 is going to be f of 2 minus 1, so f of 1 times 2. So that's 8 times 2, which gives us 16. And this is like my a to the n minus 1 from up here. So now we have the third value, so we want to use a2, which was this guy, times 2, so 32. Now we're going to use this one, so 32 times 2, which is 64. And then again, we refer to the previous one, so 64 times 2, that's 128. And we know that between each, right, because it says right here, we multiplied by a 2. So f of x is equal to, and we can use the same trick as before, 8 times 2 to the n minus 1 power. So for the first one, f of 1, 8 times 2 to the 0 power gives us 8 times 1, which is 8. For f of 2, we've got 8 times 2 to the first power, right? Because 2 minus 1 is 1. So that gives us 16. F of 3, 8 times 2 to the second power. So that's 3 minus 1 gives us 2. So that's 4 times 8, which gives us 32. 8 times 2 to the 4 minus 1, so that's the third power. And that gives us 8 times 8, which is 64. And then f of 5, so 8 times 2 to the 5 minus 1, or fourth power. And so that's 16 times 8, which is 128. So all of our numbers match. It looks like the recursive formula for this is indeed f of x equals 8 times 2 to the n minus 1. That's the nice thing about geometric sequences. They just happen to be related by a constant number. So if you have any other questions, feel free to let me know, and hopefully this helped you out.